Alright, so we're doing the exam review. We're starting with quiz number 1. Alright, number 1 is just a combination question. You should know how to do that if you have to, particularly because you may have to do it for question 2. So let's do question 2. 5% of welds done by welding robots at Arbitron Lewis Bird Manufacturing are substandard and need to be redone. Suppose you randomly choose 5 recent welds. Use the binomial function to compute the probability that exactly 3 of the 5 welds are substandard. So we have a formula for this. We're going to pick 5 random welds. We know at each time we pick, there's a 5% that one of those welds is substandard. And we're going to, if you remember the way we term the binomial formula, we're going to call that 5% chance of success. A little weird because we're actually talking about substandard and using success to mean that. So probability of 3 successes equals, number of combinations out of 5 total. How many combinations of 3 could we have? This could be the first 3, the last 3, the first, third, and 5th one. We don't care. Just how many different combinations of 3 out of 5 things could we have? Times chance of success happens 3 times, raised to the 3rd power, times chance of failure happens twice, raised to the 2nd power. Alright, this combination thing, we just use the combination formula. Was it 5 factorial over 5 minus 3 factorial divided by 3 factorial? Just remember to do the 5 minus 3 and then do the factorial. And then multiply those together and divide that by whatever you get after you do the whole 5 factorial. Multiply that whole thing out and we get 0.11%.
Wait.
Yes.
So what you did right here, the 5 factorial, right?
Yep.
Once I get that answer, I'm going to multiply by 0.5 to...
Yeah, that's right. Exactly. Now let me just write it again. So it's going to be times 0.5 to the 3rd times 0.95 squared. Does that make sense? Write it out this way.
Is this combinations?
This is combinations, but this is a binomial function. Alright, probability of this number of successes. Use this formula. Alright, we good? Alright, the production of cars per day at an assembly plant has a mean of 120.5 and standard deviation 6.2. Find the probability that fewer than 110 cars are produced on a random day. Assume the distribution is normal. So this is before we learn about the sampling distribution. This is just where we need a z-score, and then we look at the z-table and find the area associated with that normal distribution. And we know this is a normal distribution because it says assume the distribution is normal. So let's get our z-score. Alright, so the z-score for 110, z equals 110 minus the mean, 120.5, divided by standard deviation, 6.2 equals negative 1.69. Alright, so if this were normally distributed, alright, 110 cars would be 1.69 standard deviations below the mean. Alright, what are the chances of that happening? Well, we can figure it out because statisticians know what the normal distribution looks like. It's the same whether you're doing cars, height of trees, size of babies, whatever. We can look on the z-table and figure out the probability of getting that or lower. So we look for 1.69. We find the answer to be 4.6%. Any questions? All right, outstanding. For number 4, Yeah, if you won't have to do standard deviation for the exam, but if you did, you would just use Excel. And if you need it in the future, you'll just crunch it in Excel. Number 5, the income with the skewed distribution. I hope that was a good exercise in thinking about a non-normal skewed distribution and what you can infer from a few basic points of information. But you won't have a question like this on the exam.
Or number 5?
Yeah, number 5.
So it won't be.
Will not be on the exam.
So 1, 2, 3, yes, 4, 5, no.
Wait, but you said it's only 10 questions. So one of the first. One of these will be.
You're assuming that I picked one from each quiz.
I don't know because there's only 8 quizzes.
There's only 8 quizzes.
Basically,
So yes. So yeah, I mean that would make sense to me. Approximately one from each quiz, and then
It's an easy one.
yes. All right, class quiz 2. All right. Number 1 was the tricky multiple choice one, which got us used to thinking about the sampling distribution and the sample mean. So if you want to reread that and think about that for fun, I'd welcome you to do that. But all it's saying is there's a difference between the sampling distribution and the sample mean, and a question like this where we can infer specific probabilities of the population. So let's not get into that discussion. Let's move on to number 2. Before any order is shipped, inspectors at Alvarez Manufacturing test the sample units for breaking strength. You select a random sample of 49 units from a recent order and find that the average sample breaking strength is 814. Assume the standard deviation for the population of units of the order is known to be 35. Construct a 95% confidence interval. So what does that mean we know the population standard deviation? How does that help us? So, all right, so we've got a sample mean of 814, and we need a confidence interval. So we have 814 plus or minus some amount. And this is, so we're going to need 2 things. We're going to need either a z value or a t value, and we're going to multiply that by our metric for standard error. So, question again, since we know the population standard deviation to be 35 pounds, how does that help us? Yes, since we know the population standard deviation, Jonathan, we can use the z value. All right, so what's the z value we want for 95% confidence interval? 1.96. Fantastic. Times our standard error figure. So standard error is going to be 35 divided by the square root of 8. Remember when we use the sampling distribution, that standard error gets tighter. Tighter based on a larger number of samples. 49. Okay, does that all look good? So we know we can use the z. We know the appropriate z value for 95% is 1.96, and this is our standard deviation of the sampling distribution of the sample mean, also known as the standard error.
Is that square root?
Yeah, square root of 49 is 7. 35 divided by 7 is 5. Yep. So 1.96 times 5 is about 10. So our confidence interval is going to be about 804 to 824. Not 5,000. Yeah. Yeah. All right. So confidence interval is 804.2 to 823.8. Uh, 8.402. Okay, 804.2 to 823.8. Any questions there? All right, let's do number 3. TradeLine is an online stock trading service. To estimate the average number of trades made last month by TradeLine's clients, you take a simple random sample of 121 clients and find the average number of trades in the sample is 45.8. Since you do not know the population standard deviation, you calculate a sample standard deviation of 12.3. Show the 95% confidence interval for the average number of trades of all TradeLine's clients. So you're looking for a confidence interval for the average number of trades. All right, what's your point estimate for average number of trades? Point estimate? 45.8, yes. So that's, if you had to guess, gun to your head, you'd say 45.8. But that's just an estimate. So you want a confidence interval. So you're going to do a plus or minus, some sort of z or t value times some sort of standard error. Now, since you do not know the population standard deviation, what does that tell you? T value. All right, so what t value are you going to use for 95% confidence, 121 samples?
Minus 120
Yep.
degrees of freedom.
Degrees of freedom is now 120. And if you have 120 degrees of freedom, you're going to look on the t distribution for a 95% confidence, and in this case it turns out to be 1.98. Very, very similar. 1.98 to the z. But you should be cognizant of the fact that you need to use the t. Gives you a little bit wider interval because to account for the unknown factors. And then, of course, your standard error is 12.3 divided by the square root of n times 12.3 divided by the square root of 121. Okay, so that's 12, square root of 121 is 11. So 12 divided by 11 is a little bit bigger than 1. So 1.98 times 1 is about 2. So 45.8 plus or minus about 2 is going to give us 43.59 on the lower end, 48.01 on the upper end. Make sense? Like this? Good? Good? Excellent. All right, ready to move on to class 3? All right. So for class 3, we're going to do confidence intervals for proportions, mean differences, and proportion differences. So for number 1, we're looking for a proportion confidence interval. We take a random sample from a large proportion and find the proportion to be 40%. Sample size is 500, 95% confidence interval for the upper and lower bound. All right, so what's our point estimate for this proportion? Point estimate for this proportion.
0.022? No, 0.04.
Yeah, 0.4.
0.4.
All right, so 0.4. So we need a plus or minus. Now, if you remember, statisticians are all okay with you using the z distribution for proportion confidence intervals. The reason being that you don't have standard deviation in the same sense for proportions. If it's just a yes or no, you don't have these really extreme rich people throwing the distribution off. You just have yes or no. So proportion doesn't really, or standard deviation doesn't exist the same way. When we get to the sampling distribution, we just use a mathematical estimate of what the standard deviation would be based on how close the proportion is to 50%. So we're okay with using a z distribution. So we need some sort of z value for 95% confidence, what would that be?
1.96.
Yes, 1.96. And then, if you recall, we have this kind of funny standard deviation of the sampling distribution of the sample proportion. It is the sample proportion, 0.4, times 1 minus the sample proportion, 0.6, divided by the sample size, which is 500, right?
Yes.
500.
All square root.
Yes. All right. So 40% plus or minus 1.96 times this. You do those numbers, it turns out to be yeah. Turns out to be about 4%. Yeah, 0.022. So this right here turns out to be 0.022. And remember, this is 2%. So just because it's 2 decimal places, don't round this off. You want to keep this whole number in your calculator or in Excel, because 2%, this is pretty significant, even though it just looks like it's a fraction number, because we're in percentages. So 1.96 times 2% is about 4%. So 40% plus or minus about 4%. It's going to be your confidence interval. So if we take 40% plus or minus 4%, we get 35.7% on the low end, 44.3% on the high end. All right, think about that for a minute while I erase and make some room. All right, we ready for number 2?
Yes.
All right, so what are we doing in this one? We're looking at mean differences. I want the mean difference between population 1 and population 2. So I'm going to take a sample from population 1, sample from population 2. I'm going to get sample means for both of them. And I'm going to have a point estimate for the difference. And I'm going to have some big crazy formula for the standard deviation of the sampling distribution of the sample mean difference. And if you remember from mean differences, statisticians say go ahead and use the z distribution for confidence intervals, because there's so many moving parts for mean differences. They say it's probably all going to cancel out. Just go ahead and use the z distribution. So in this case, we've got sample sizes of 1,500 from both populations. The mean of the first sample is 76 with the sample standard deviation. The mean of the second sample is 68 with the sample standard deviation of 18. 90% confidence interval. All right, what is our point estimate for differences between these two means? Help us out, Jada.
Yeah, the data. 2.
Point estimate for the mean difference. 2 is a good guess, but
Oh, that is point 0.02.
where are you getting 2 from? All right, well, what's the mean of, when the mean of one sample is 76, the mean of the other sample is 68, what's the difference? 8, yes. So 8 is our point estimate for the difference. And since we want a 90% confidence, we want to plus or minus some z value times some standard error figure. All right, now z value, we're cool with using z value because we can do that with mean differences. There's so many moving parts. Statisticians say go ahead, use it. What z value do we want for a 90% confidence interval? 1.65. Fantastic. And then we have this crazy formula we need for the standard error. And it is the sample standard deviation from population 1 squared divided by sample size 1 plus standard deviation from sample size 2, sample 2 divided by sample size 2, square root all of that. And that's it.
That's the fine standard error.
Yeah, this is standard error. You could also practice saying the whole thing out just to get used to it. Standard deviation of the sampling distribution of the sample mean difference.
Can you say this slow?
Standard deviation of the sample distribution of the sample mean difference.
It's written there.
All right. Cool. So when we crank all that out, do the plus or minus, we're going to get on the low end 6.8, 6, and on the high end 9.14. All right, we good there? All right, now we want to do proportion differences. So we've got 2 golf balls being tested, or correction, 1 golf ball being tested. And we're going to have the pro golfers check it out. We're going to have the amateur golfers check it out. And we're going to see, is there a higher percentage among one group? If there is, we may want to concentrate our marketing efforts there. If there's no difference, we may just want to concentrate our marketing efforts on everyone equally. So we take 100 pros, 100 amateurs. The pros say they like it at 78%. The amateurs say they like it at 64%. We want a 90% confidence interval for the difference. All right, what's our point estimate for the difference?
Is it 8% again?
I think they're on the right track, but I
I'm sorry.
think that is
14.
terrible. Wow.
14.
14.
Yep. So 14 is our point estimate, just a point estimate. So we want plus or minus something.
Which is going to be the Z or T score.
Yeah. For proportions, we're always okay with using Z because standard deviation doesn't have the same significance in proportions. So statisticians just calculate standard deviation based on math. So they say, go ahead and use the Z. So what Z are we looking for 90%?
1.65.
Yes. 1.65 times our standard error figure, also known as the standard deviation of the sampling distribution of the sample proportion difference. Okay. That's 0.7. All right. Proportion 1 times 1 minus proportion 1. 0.2. Yes, Barbara. Divided by N1, which is 100. Plus proportion 2, 0.64, times 1 minus proportion 2, which is, what is that, 0.36, divided by N2, which is 100, square root that whole thing.
That's 0.78 times 0.22 or
0.78.
Yeah, 0.78, so proportion 1 times 1 minus proportion 1 divided by sample size 1. Proportion 2 times 1 minus proportion 2 divided by sample size 2.
Wait, can you, you don't have a 1 up here. Here we have a 1. Is,
Yeah, I just I could do that.
no, but no, I'm asking you, what, the 1,
1 minus 0.78.
that's the remainder from 100.
What's 1 minus 0.78? Yeah. 1 minus 0.78 equals 0.22. Yes, Sam.
Just to clear something up really quick. We do 1 minus 0.78 because we do not have the sample standard deviation?
Well, there is no standard deviation with proportions. Remember, it's just a yes, I like the golf ball, or no, I don't like the golf ball. So with proportions, standard deviations doesn't mean anything.
So we're always going to do, for proportion standard deviations, we always do the 1 minus 0.78.
Yeah, we just always do the math formula, which is this for differences, but it's just half of this for if it's just a point estimate for a confidence interval for one proportion. Does that make sense, Andrew?
Carlos asked me, and I was double checking.
Oh.
But I was
Because
wrong.
it's just the difference between question 2 and 3. Well, we
Oh yeah. Well, question 2 is mean differences.
mean difference.
Yeah.
So with proportion differences, that's when we have to add the extra step of the 1 minus the sample proportion.
Well, see, here's I wouldn't say there's really an extra step. For mean differences, we have some z or t value times a standard error figure. And for proportion differences, we have some z or t value times a standard error figure. But the reason why in mean differences we're using standard deviations from each of the individual populations is because they exist. Like this is a standard deviation of population 1.
Right.
It's 20.
Right.
Like it's there. If we were to calculate it, we would find it. It may be income levels, or what is, I don't even know what it is in this case. It's undefined in this case. Maybe income levels, it may be IQ, it may be whatever. And so there's going to be a standard deviation of population 1, standard deviation of population 2. So we use that to calculate the standard error. But for the proportions, all right, this is just 78% said yes. For the weekend golfers, 64% said yes. So that's all we had. And that's all we know. They said yes or no. We had no way to quantify whether it was an extreme yes or an extreme no. So there was no such thing as standard deviations for proportions. Remember I gave the example which was funny like a month ago but not so funny today, where if someone asks you, are you voting for Donald Trump? All you can do is scream no into the phone really loud,
Yeah.
and then they put you down as a no vote. They're not like, that's an extreme, it's just yes or no. There's not an extreme no, not an extreme yes. There's no standard deviation there. Okay, so when we crank all of that out, we're going to get 14% plus or minus some amount. And it's actually going to come out to about 10. Right, about 10%. So it's going to be about, between 4% and 24% is going to be our confidence interval. So specifically, it's going to be 3.6% on the low end, 24.4% on the high end. Make sense?
Yes.
Good? Fantastic. All right, let's move on to class 4. Hey. All right. So, p-value measures the probability that if the null hypothesis is true, we would randomly produce a sample result at least as unlikely as the sample result that we actually produced. So that is p-value. What's the probability of producing that sample result, assuming our null hypothesis is true? And you heard me say like 50,000 times that the key to hypothesis tests is we're always assuming the null hypothesis is true. We said if what that realtor said is true, then there's only a 3% chance of this happening randomly. So I think that's enough to go back and throw a rock through his window. There's only a 3% chance that I could be wrong. I'd be like, I feel so bad. I threw a rock through your window without,
There's only a 3% chance that he could be wrong.
There's only a 3% chance that you could be wrong if you throw a rock through his window. We'll talk about that for a minute, because I know it gets really confusing the way you look at it. And Victor, specifically, we said with the starting point, if what the realtor says is true, and then our sample result came back to be something different, the realtor could still be telling the truth, but there's only a 3% chance the realtor could be telling the truth in this manufactured example. Okay, so type 1 error is reject. I don't even remember what a type 1 error is. So just read that. I think type 1 is rejecting a true null. Yes. Yes.
Are we getting true and false?
No, you're not getting a true false. All right, you would get a question like question number 3, so let's do that one. Bottles at Laguna Falls should contain on average 15 ounces of liquid, no more and no less. You select a sample of 36 bottles that has a mean of 14.915 ounces per bottle. So Laguna Falls said 15 ounces, no more, no less. And your sample, 36, comes out to be 14.9. Well, let's do some further investigation and see if you can reject the null hypothesis that the mean is 15 ounces for the population of all Laguna Falls bottles. Use a significance level of 5% and assume population standard deviation is known to be 0.15. All right. So, let me do some erasing here. All right. Null hypothesis. The mean equals 15, no more, no less. Alternative hypothesis is what? Not equals 15. All right. Is this a one-tailed or two-tailed test? Two-tailed test because there are two ways I can disprove this, either with a high test statistic or a low test statistic. So let's find, one, what our test statistic is, and two, let's define what our critical values, what our cutoff point would be for what we're willing to believe. Let's start with the critical values. The cutoff point for what we're willing to believe. Before we go back and throw a rock through the window of Laguna Falls watering. We want a significance level of 5%. What's that going to mean for our critical values?
1.96.
Yes, 1.96 is correct, and that's going to leave us with a 2.5% chance of getting it wrong on the low side, a 2.5% chance of getting it wrong on the high side, for a total of 5% chance we could get this wrong if we're willing to say your null is false. So negative 1.96, positive 1.96. All right, that's our cutoff value. Anything more extreme than that, we're like, fool me once, I'm not believing that. Anything more extreme than that, we reject what Laguna Falls says is true. So we now need our test statistic. So we want to know how different this 14.915 is under the assumption that what the company says is true, that the true mean is 15. And specifically, we want to know how many standard errors it is above or below. And our standard error figure, we can use the sampling distribution of the sample mean to calculate that. We know that the full population standard deviation is 0.15. We get to make it smaller than that, because we get to take that divided by the square root of the sample size, 36. All right. When we crunch all of that out, we get a test statistic of negative 3.4. What do we think of that? Yeah, so this negative 3.4, it's going to fall way over here into our rejection region. We decided anything more extreme than negative 1.96, we are not going to believe that the mean in the whole population is 15. So we reject the null hypothesis and assume the alternative hypothesis. All right, good. Fantastic. All right, let's do some more hypothesis tests. Young and company claims that its pressurized diving bell will, on average, maintain its integrity to depths of 2,500 feet or more. Like our bell will maintain integrity to at least 2,500 feet, maybe even more. All right, so you take a random sample of 50 bells, and you find that they have an average depth where they lose integrity of 2455. So you have a little bit of evidence to the contrary. They say 2,500, bells will maintain their integrity, but you find bells start losing their integrity on average at 2455. Question is that overwhelming evidence to the contrary? So let's set up that hypothesis test. Let's get some critical values. And let's decide if we're going to reject based on the test statistic you compute. So what is our null hypothesis?
Look, if the mean is greater.
So the mean in the whole population is greater than or equal to 2,500 feet. So let's assume what they say is true.
I'm sorry, really quickly.
Yes.
What's the key word that tells us it's greater than or equal to? Or does it actually say that?
Feet or more.
Yes, it says they claim on average feet, feet or more is the key word. Maintain its integrity to 2,500 feet or more.
Oh.
All right, so what's the alternative then?
Is less than
2,500. All right. So let's find a sample mean, see what we get. All right, we do our sample mean, we get 2455. We have evidence to the contrary. Only question is that overwhelming evidence to the contrary? Well, out of a sample of 50, we can also sample of 50, and we know the population standard deviation of 200. How does knowing the population standard deviation of 200 help us? What's that?
You would find the sampling distribution of the sample mean.
Yeah, well, you could anyway. You could always find the sampling distribution of the sample mean, but knowing the population standard deviation allows us to do one thing that we wouldn't be able to do if we didn't know that.
P-value?
T. We can now use. We can use the z-stat because we know the population standard deviation. If we didn't know this, then we would have to use the t table. All right. So, all right. What's our next step? Now we want to get that z-stat. So, z-stat equals, all right, 2455 minus 2,500. What's the difference between our sample mean and assuming what they say is true, 45? How many standard errors is that below the mean? Well, what's our standard error figure? It is our population standard deviation divided by the square root of our sample size, 50. Okay? Is that good? And what do we get when we crank that out? negative 1.59. Okay, so that's 1.6 standard deviations below the mean. That seems pretty significant. That's not 3 standard deviations below the mean. So let's get an exact method of saying whether or not we want to reject this null hypothesis or not, and let's do it with our p-value. Let's find the probability of getting a test statistic at least this extreme. How do we find p-value? On the chart, absolutely.
One minus that. Oh yeah, you find the area of that, and then you do 1 minus that.
0.559.
0.55, wait a minute. 0.0559?
Yes.
Yes, 0.0559. So in this case, you don't need to do 1 minus because you're looking at the negative. If you were looking at the positive, you might have to do 1 minus. But, so, if we're looking at the z table, and we're able to look directly at negative 1.59, the z table will actually give us this area. That's what Joseph Mel just read to us. All right, that's about a little higher than 5%. Sometimes, if it's positive, it'll give us, it'll give us all this area, and 1.59. And if we wanted this, we would have to do 1 minus.
Wait, you said if it was positive, it would be everything behind?
Yeah, if you're look up 1.59 on the positive side.
Oh yeah.
Gives you 94 something.
Point,
Yeah, so that's what that's 90. So this giving you 94 here. All right. So if you wanted this, then you have to do 1 minus 0.94. Okay. So we've got a p-value of 0.0559. What is our fail to reject decision? Oh, actually, let me back up 1 minute. Is this a one-tailed or two-tailed test?
It's 1
It's one-tailed. Do we need to do anything with this point?
No.
0.05? We do not because it's a one-tailed test. So what's our decision? Yeah, fail to reject. Yeah, because the chances of getting something as extreme as this are 5.5%. And we decided anything over 5% will give you a pass. We'll say, fine. What you say could be true. But if there's less than a 5% chance of getting something that extreme, we're going to say, we're not believing it. We're going to reject the null. If this were like 0.03, we would reject the null. Yeah, you're right. The actual answer is fail to reject. Yeah. Yeah. Absolutely. All right. We ready for the next one? Number 5. Yeah, let's do number 5. All right. From a recent production run of portable generators, you select a random sample of 10, small sample size. You find the average run time for units in the sample is 24.4, with a sample standard deviation of 0.6 hours. Use the sample results with 5% significance level to test the null hypothesis. The average runtime for the full population of generators is precisely 25 hours, no more, no less. All right, let's start with that precisely 25 hours, no more, no less. What can we do with that?
It sets up our null hypothesis to be equal to or not equal to.
Exactly. So precisely 25 hours.
Which means it's a two-tail.
Yes. the mean, so the company says their average runtime is 25. Alright, let's set up the alternative as if the average runtime is not 25. Two-tailed test, because there are two ways to disprove this. Alright, so let's see. We've got a couple things to consider. One is we have a sample size of 10. The other thing is we have a sample standard deviation of 0.6. Let's start with this one, the sample standard deviation of 0.6. What information does that give us? Yeah. Yeah, we're going to use a t-stat at the very least. And then how about this sample size of 10?
10 minus 1.
Yeah, that's going to give us degrees of freedom 10 minus 1. But there's a nuance here, and I'll just spend like 30 seconds on it. If it confuses you, don't worry about it, but I think it's worthwhile. So this is less than 30. And if you remember, we said we can only use the sampling distribution of the sample mean or only assume that's normal if we have a sample size of more than 30. So
you're saying that
So
if
this
it's more
is
than
not a
30,
normal distribution, potentially.
unless we have a critical piece of information, we could not assume that the sampling distribution of the sample mean is normal. Well, we're not even to the reject or don't reject. We're stuck. There's nothing we could do. And if we can't assume that the sampling distribution of the sample mean is normal, we stop. Okay, I can't do anything. I need at least a sample size of 30 or more. But this question tells us something that gives us permission to keep going.
you select a random sample.
Oh, it's precisely 25 hours.
No. The last sentence.
Yeah, so no, yeah.
Oh,
No,
normally distributed.
Yeah. Assume is normally distributed. But does that give us permission to use the z distribution?
No,
Just, we still have to use t because we don't know the population standard deviation. But now we can assume that the sampling distribution of the sample mean is normal. All right. All right. So let's get our standard error. All right, that's going to be our 0.6. 0.6 divided by the square root of the sample size is going to be 0.190 is our standard error. All right. So let's set up our critical values. All right, this is going to be a t distribution. And we're looking at a significance level of 5%. All right, so how are we going to decide on critical values here? We're going to need sample size of 10 is going to be one thing that's going to help us. And the fact that we're using a t distribution is also going to be important. So degrees of freedom is what? 9. All right, and if we're looking at a t distribution two-tailed test, we're looking for 2.5% in either tail. And we'll look on the table, and we'll find those critical values. And if you're looking in the back of the book, you would find them. If you want to do that now, you can. Otherwise, you can just look at the answer. And it's going to give us negative 2.262 and positive 2.262. All right. So all we need now is our t statistic. Make sense, Josima? Good. All right, so our t-stat equals, all right, our calculated, oh wait a minute, I forgot to put down, we had a calculated mean of 24.4. How different is that from what the company claims is true? What's the difference between that and 25? In particular, how many standard errors difference is it? Yep. And what's the t-stat we get when we crunch all that out? Negative 3.16. All right. So what do we conclude, Barbara?
That you reject the null because it's outside of the clinical value.
Outstanding. So we're here. We reject the null. We assume the alternative mean does not equal 25. All right. You're feeling good on this?
Yes, sir.
Excellent. Quiz 5. All right. So here we're going to continue doing hypothesis tests, and we're going to look at proportions. We're going to look at mean differences, and we're going to look at proportion differences. And we know how to do all that because we learned them in previous classes. Now we're just combining hypothesis tests with proportions, mean differences, proportion differences. So suppose, for number 1, in past years, students at State U, or administrators at State U, claim that at least 20% of their students choose to pursue public service careers after graduation. For an editorial piece on declining student commitment to such public service, the school newspaper surveyed a simple random sample of 400 students and found that only 56 of them expressed an interest in a career in public service. Now, what percentage is that? 56 out of 400.
Like 14.
14. Okay, so in past years, the administration claims 20% or more of our students are going into public service. The newspaper finds only 14%. So that's a little evidence to the contrary. Question is that enough to assume if they were to survey the entire population of every single student, would it be less than 20? Or is this 400, sample of 400, a statistical anomaly? So let's set up a test and question, does this sample result provide statistical evidence of a decline in student commitment for the population of students currently enrolled at State U? That is, can the sample result be used to reject a population proportion greater than 20% null hypothesis? Use a significance level of 5%. Okay, so I don't think I actually I realized when I was going through this on Monday night that I didn't actually put the null and the alternative hypothesis in the answer, so we'll get to do it now. What is the null hypothesis we're looking at?
Greater than or equal to 20%.
Yes. Proportion greater than or equal to 20%. And what's the alternative?
Proportion less than or equal to.
Yes.
Or just less than.
Yep, less than 20%. All right, so we're going to need a test statistic. To get that test statistic, we want the standard deviation of the sampling distribution of the sample proportions. And then for this question, we're asked to find a p-value, and then we can make a reject, fail to reject decision. So let's start with the standard deviation of the sampling distribution of the sample proportions. All right, so in calculating this standard deviation, do we need to use standard deviations from the population, Andrew?
This sample?
Yes.
Not.
No, why not?
It's a sample.
Well, should we take standard deviations from this sample? Can we take standard deviations from the sample?
No, it's just proportion.
It's a proportion.
Yes, proportions. Standard deviation doesn't exist. So, we're going to use this mathematical formula to calculate the standard deviation of the sampling distribution of the sample proportions. Alright, standard deviation, sampling distribution, sample proportions equals, assuming the null hypothesis is true, 0.2 times 1 minus 0.2 divided by the sample size, square root all of that, and that's going to come out to 0.02. 2%. Alright, that is our standard error figure. 2%. So let's calculate our test statistic. We're comfortable using the z distribution because proportions don't have standard deviation the same way. We just use this mathematical formula. So let's find the z stat. Okay, what is our proportion of students who are going into public service in our sample?
20%.
What's the one we calculated, or the student newspaper count calculated?
0.0.
No, 14%.
14%? Yep. Let's find the difference between that and assuming what the administrators might claim is true. So that's 6%. Then let's find out how many standard errors difference that is. And we calculated the standard error, 2%. So that's going to give us -3. 3 standard deviations below the mean. And we're using the z-stat. It sounds like a lot, right? A whole 3 standard deviations below the mean.
99.7.
Something in there. Yeah, something crazy like that. So let's calculate the p-value for a -3 z-score. How would we do that? Josemel? Yep, find -3 on the table. And what do we see when we look at -3 on the table?
0.0013.
Yes. Equals 0.0013. Do we need to multiply that by 2?
No, because it's a 1.
Right. Okay, so good. So our p-value is 0.0013, which is 1/10 of 1%. What is our fail to reject decision? Given that our significance level is 5%.
I'm sorry. Ask that again.
Okay, so our p-value is 0.0013. Our significance level is 5%. What is our fail to reject decision?
No, sorry, yeah,
We reject. Yes, it is so unlikely to get a -3 test statistic, 3 standard deviations below the mean, if what the administrators say is true. And we interviewed 400 students, and we were able to get a pretty tight standard deviation, and we were able to determine that it would be 3 standard deviations below the mean if what they say is true. There's only a 1/10 of 1% chance of that happening. Let's reject what they say is true. All right, makes sense.
So the exam is going to be the same or different? If we have this, there's no reason why we should.
Right, I agree with that. Same wording, different numbers. It may be, I could change it around. It might be a 2-tailed test. It might be a little bit different. Like you need to use a t distribution in the quiz, but you need to use a z for the. So there might be a couple differences like that. All right. So let's do number 2. All right. An agriculture study done. We're good to move on? Good to move on? All right. An agricultural study done to examine the impact of using a new mix of pesticides on Canadian canola crop. 459 farms used this new pesticide, and a sample of 295 farms used the old pesticide. All right, the average revenue for the new mix farms was $155. Average revenue for the conventional mix was $152.10. So the new mix farms are making a little bit more revenue per acre. Question is that just happening by chance because of the sample size? Or is there truly a difference between the mean revenue for all the new mix and the mean revenue for the whole population of all the traditional mix farms? So, we want to think about the point estimate difference of about $3. We're going to think about what our standard error figure for the mean differences would be. We're going to set up a hypothesis test. We're going to calculate a test statistic, and then we're going to calculate a p-value. Then we're going to make our decision. So, let's see. Alright. So, that standard deviation of the sampling distribution of the sample mean differences, let's be sure we're comfortable with that. And then once we're comfortable with that, we should be able to breeze through the rest of this problem. So, where's that coming from? Sampling distribution, standard deviation of the sampling distribution of the sample mean differences. Yeah, but just, I mean, just what can you tell me about that? Just without getting into numbers. How is that going to help us? Standard deviation of the sampling distribution sample mean differences. So we're going to have a point estimate for the mean differences, and we calculated that to be about $3, or we're going to. $1.55 for the new mixed farms, $1.52 for the old mixed farms. So it's about $3. How many standard deviations difference is that? Considering if we were to do a no difference null hypothesis. All right, I realize, Justin, don't worry so much about that. I feel like that was a complicated question I posed. Let me erase this, and then we'll set up the hypothesis test, and then I think we'll be in good shape. All right. So, what kind of null hypothesis do we want to set up for this question?
Equals with the number.
Go ahead, Barbara.
Oh no. Figure it out. It's a one-tailed.
All right. Look in the question for some of the wording. Yeah, it does say construct a one-tailed hypothesis test to determine if these sample results are sufficient to reject a null hypothesis. The average gross revenue for new mix is no greater than the average gross revenue for conventional mix. So it's saying the mean of new is less than or equal to population mean of conventional. Okay, so this is the conventional mix, this is the new mix, and it's saying, let's assume that the new mix is the same or worse. And the reason we might be setting it up this way is because we might like this mix and we want to market this new stuff, and we can say we did a hypothesis test assuming no difference or worse, and guess what? We found overwhelming evidence that this new mix brought in more revenue. All right, and that overwhelming evidence would be the alternative hypothesis that the mean for new is greater than the mean for conventional in the whole population. So let's remember when we're doing mean differences too, what distribution do we get to use? Z. Z. Statisticians say there's so many moving parts, just use Z. It's good. All right, so our Z stat is going to be our difference between the new mix and the old mix. So 155 minus 152.1. All right, so the difference, and that's going to be about $3. And we want to know how many standard deviations difference that is. All right, because if it's just a half standard deviation, that's not much. If it's like 4 standard deviations, then we're like, whoa, we have overwhelming evidence that there's a difference between the new and the old. So now we need a standard deviation figure for mean differences. So, what do we do to get that? Yeah, that's right. The standard deviation of the sampling distribution of the sample means. And we've got a formula for that. You just want to have that handy. All right, and it's a big complicated formula of, let's see, it's the standard deviation of population 1 squared divided by sample size 1 plus standard deviation of population 2 squared divided by sample size population 2, square root that whole thing. Okay? So once we do all that math, what do we come up with? 0.49. All right. So just eyeball that. Tell me what you think. That is the answer to the question, what is the z-stat? Well, the answer is 0.49. We got that by taking the difference between new and old. How many standard deviations greater is the new mix compared to the old? The answer is 0.49. Take an eyeball at that. Tell me what you think. Is that a significant z-stat? Is that an insignificant z-stat? Remember some of the previous problems? We got -3, -3.4, but now we've got 0.49. What does that mean? Small. All right, it's just 1/2 standard deviation above what we would expect if we were to assume the null hypothesis. So we're not feeling like we have something that's going to be overwhelming evidence just by looking at 0.49. But let's get a p-value so that we can be a little more scientific and exact. What would be the p-value associated with a z-stat of 0.49? Yes. How would you find that if you were looking on the tables, VK?
I would look up to 0.49.
Yes.
And then you plug your number.
Yes. You look up 0.49, and in fact, what would you get if you look up 0.49, Josemel? What would you get if you looked up 0.49 on the table? No, on the Z table. Actually, somebody pointed out that there's a minor discrepancy on this.
0.49?
Yeah, 0.49 on the Z table. Yes.
hypothesis.
Yes.
.49 is 2.5.
I don't think so.
Oh no.
That's right.
On the Z table?
Yes.
.6879.
0.6879. Okay, is that our p-value? Yeah, how do we get from that to our p-value?
It's subtract.
Subtracted.
1 minus 0.6879. What do we get when we get that?
Because we need to get a negative. We're doing that to get that in the negative, right?
No, you do that because you're looking at this right. This is what the-
Need 3121.
Z gives you, and you want that piece right there.
Yeah, so when you look up the 0.49, it's on the z table, it's going to give you all of this, right? But what we want is this part. So we want to do 1 minus. And so when we do 1 minus, we get what, Lisa? Or somebody said, Barbara, what did you say?
0.3121.
3121. Yeah, somebody on Monday night pointed out to me that these are different. But yeah, that's partially why I wanted to take you through that exercise. 0.3121. My answer was 0.3103. So sorry about that. Okay, so in our decision, Miguel?
Oh, we're going to fail to reject the null hypothesis.
Fantastic. Fail to reject. All right. All right. Let's see. Based on, you ready to do number 3? Yeah? We're going to take a break. Keep going. Break? All right. Let's take a break. Let's take 10 minutes when we come back at 8:03.
You're taking it now.
All right.
Let's go. Zach waiting for us here. Let's
Restart.
let's simmer down.
Actually, no. It sounds like you all are having more fun. Let's just let's talk about that instead. You all pretty much have the answers here, right? You just go home. Call it
day.
You
Call
stuck
it
with
a
us this
day.
long, Zach. Come on. Last class. Don't give up on us now.
Okay.
Last class.
All right.
Almost done.
Okay, so Fannie Mae
Long
and
class
Freddie
as
Mae,
Where are you?
number 3 on quiz 5.
Oh, okay.
Fannie Mae says that there are differences in knowledge between college-educated and high school-educated homebuyers. So they conduct a sample and find that 62% of college homebuyers know something about a mortgage. Only 60% of high school homebuyers know something about a mortgage. And we've got a sample of 500 college kids and 259 high school kids. With regard to this particular issue, can you use the sample results to reject the no difference in population proportions null hypothesis for the two populations represented? All right, what does that mean, reject the no difference in population proportions? I'll give you a hint. It's going to tell us something about our null hypothesis.
It doesn't matter what your education is,
Yeah.
whether or not you understand the mortgage.
Exactly. That is a brilliant way to say it. How would we represent that with proportions and equal signs?
Um,
All right, I'll give you a hint. It's proportion, college. Start you off. It doesn't have to be V. Gale. She answered the first part of the question. It could be someone else. Null hypothesis is proportion of college kids. This is the whole population. Is it going to be greater than, less than, or equal to?
Greater than. No.
Sorry, Carlos. Sorry, was that too? All right, so a no difference hypothesis.
No.
Equals, yes. I'm sorry, I shamed Carlos into looking down, but he's got it.
I was rereading.
I'm sorry about that. All right, no difference. You could never fail me, Carlos. Never ever. Never ever. You're the one who invented p-value.
I was here.
Here, Jonathan Herms. Carlos invented p-value. Let's never forget that. Alright. Proportion of college kids is the same as proportion of high school kids in the whole population. Alternative hypothesis, proportions not equal. Alright. Ready? So, one-tailed or two-tailed test?
Two-tailed.
Yes. Two-tailed test. There are two ways of disproving this hypothesis. So, we've got a difference in our college sample of 62 and our high school sample of 60. So, remember we can always use a z-stat in proportions. Everything's cool there. So, our z-statistic in evaluating this null hypothesis is going to be 0.62 minus 0.60 divided by our sampling distribution, our standard deviation of the sampling distribution of the sample proportion. All right, and to do this, to get this sampling distribution, standard deviation of the sampling distribution, I guess I forgot to put standard deviation on the answer. So the third line of the answer, it should say standard deviation of. Standard dev of. Standard deviation of the sampling distribution of the sample proportion. Difference. Got it. Yeah. So 2 mistakes on that. Sorry about that.
You better be.
Yes. So there's a little nuance we need to take care of to get that figure. First thing we need is the pooled sample proportion. So we do a weighted average, 500 people in the 62%, 259 people in the 60%. What is the weighted average of that? Well, that's what the first 2 lines are calculating. Yeah, and it's 61.32%.
That's the P-bar pool.
Yes.
Pool.
P-barred pool. Yes, P-barred is the sample proportion pool. All right, and then when you got those 2 notations, that third line should start standard deviation of sampling distribution of the sample proportion and should end difference. So interject a difference. So standard deviation of the sampling distribution of the sample proportion difference. That's how that line should have read. And that's going to be our pooled proportion times 1 minus the pooled proportion divided by sample size 1 plus pooled proportion times 1 minus pooled proportion divided by sample size 2. Square root that whole thing, and we get, 3.73%. So 0.0373. Okay, and that test statistic is going to come out to 0.54.
Test that or Z-stat?
Z-stat.
I said test statistic. I could have also said Z statistic.
Okay.
Test is general. I'm willing to admit when I'm wrong, but I didn't say T statistic. That would have been definitely wrong.
Yeah. Statisticians would not allow it.
Well, actually, statisticians would say you're being a little bit more conservative. Fine. But you don't have to be that conservative. Okay.
Done.
Good point, Jonathan. So what do we do from there? 0.54. What is that? Just give me an eyeball on that. What do we think about how that's going to determine reject, not reject? So assuming the null hypothesis is true, is this a crazy result? No. No, it's only a half standard deviation above the mean, assuming that what the bank says is true. Be a little more exact, let's find the p-value. So what's the p-value for for an answer at least as extreme as 0.54? P-value. Okay.
So when we find it, are we doubling it?
Good question. So when we find it, if it's a two-tailed test, we need to double it.
Right. So when we go to Z table, we're looking for 0.54, and then we're doubling it.
Yes.
So
Yes.
0.291.
But yeah, is that what you? Okay, but then there's another nuance in making sure you're reading the table correctly. When you look at 0.54, is it going to say? What's it going to say? Well, we know it's two-tailed, and we know we double it. That's great. But when we look on the table for 0.54, what's it going to say? Like, click on the chart.
It's gonna.
I would everyone do this if I were you. I would just. Okay, go ahead. Really? On negative? Positive. Why are you looking negative? I said point.
It's a
Sorry.
positive 0.5.
Oh, it's a positive.
Yeah, it's positive.
0.705.
Okay, all right. So I made it more confusing in a way. You were jumping right to the right answer, but if you were to look at 0.54, you would get 0.7. All right. What do you do? What's the next step there? Then 1 minus that. 1 minus that gives you what?
The total surface area.
So when you look on the chart, you get what, Josemel?
0.7054.
7054. All right, and then you do 1 minus 0.7054, and that equals what?
0.2946.
2946. Are you done?
No.
Then what do you do?
Double it.
Times 2 equals
5892.
5892. Okay, and then you're done.
That's all for P.
So then the p-value here is wrong.
Yeah.
Because I said 0.5917.
Yes.
All right.
Yeah, let him know. Tell him again. Right, tell him again.
That's cool. That's cool.
But if you round that,
Wrong.
if you round that up, it's.
If we round it up, it gets to be 0.5917. Oh,
Gotta
God.
love math humor. Gotta love math humor.
Yeah. All right. I will take a closer look at that. But what for this particular quiz, I had different versions, a different quiz version. So I just cranked them all out on Excel. So there may be a difference between the Excel value I got and the answer in the table. All right. All right. So we're ready to move on? All right. Let's do it. Great work. Let's move on to regression analysis. All right, let's skip the true false stuff. You can read that in your leisure time. Let's go to question 6. All right, coefficient of determination. What's the coefficient of determination? Also known as R squared. Fantastic. And R squared tells us what? I'll start you off. The percent.
0 to 1.
0 to 1, yes. And it tells us the percent of the variation that can be explained by the regression equation. Period. You got it. Period. You got it. All right. So R squared, the same thing as coefficient of determination, percent of the variation that is explained by the regression equation. So the two components we need to answer that. The SSE is 20. That's an error, sort of left over when we draw the line of best fit. The SSR is the amount of variation that is explained if we were just to compare it to an average. And SST is total variation if we were to compare everything to just a straight average. So the two things we need for this are the SST, the total variation compared to average, and the amount of that variation that is explained with the regression line of best fit. And so to get that percentage, we take the SSR divided by SST. 800 over 1,000 is 80%. You like that? All right, another useful metric. And if you recall, there's two parts to this regression stuff. First, we take the sample data and we do a line of best fit. And we say, how well does this line of best fit the sample data? And we have coefficient of determination, we have correlation coefficient, and we're also going to recall standard error of the estimate. Those three things, they tell us how well the regression line fits the sample data. And then the next step is, what if we were to infer things about the whole population? What if we were to try to take that sample regression line and make an estimate predicting the whole population? What sort of extra confidence interval would we need to add with that? So right now we're just looking at how well does this regression line fit the sample data. And we have one metric, R squared. Well, it explains 80% of the variation. Second thing we have is the correlation coefficient, which is similar to R squared. It is the square root of R squared. A number, an R that is close to 1, means it explains it on a 1-to-1 ratio. So 1 explains it exactly. It would be correlated on a 1-to-1. Like 1 unit change in, say, time spent online would have an exactly 1 unit change in money spent
So
online.
they're directly related.
Directly related.
Okay. So
A -1 would be a directly inverse related. And something close to 0 would mean a small relationship. This correlation coefficient gives us the benefit of being positive or negative. So positive relationship, negative relationship, inverse relationship. Okay, and that's the calculation. If you take the square root of R squared, you get 0.89. All right, let's move on. Are you ready to move on to the next one? All right, standard error of the estimate. So this is a standard deviation-like figure. How well does this line of best fit the sample data? On average, how far is each point from the sample data? Well, we take the error of all the sample data squared added together is the SSE, and that's 200. We divide that roughly by the sample size, but not quite the sample size. Sample size minus 2, which gives us 4. Take the square root of that because the SSE was all squares, sum together, and the standard error of the estimate is 7.07.
So that 0.5 is square root.
Yes. Yes,
Or the sample size minus
All right, so now, once we've looked at how well this regression line fits the sample data, we want to think about how we can infer various things about the whole population, how we can predict relationship on the whole population. So now we want to calculate a 90% confidence interval for the population slope of the following sample. So what's the population slope in our regression equation? Or excuse me, what's the sample slope in our regression equation?
8.5.
Yes. All right, so that's just based on a sample. So to infer that on the whole population, what do we need? Well, we need a confidence interval. All right, so we just want to say, it's between an interval. 8.5 is going to be our point estimate, so it's 8.5 plus or minus some amount. So, and it's going to be some either z or t value times a standard error metric. So let's first talk about the z or t value. For regression, we use t value. We don't use z. So we'll just leave that at that. And how do we calculate degrees of freedom for any regression? N minus 2. And as Jonathan pointed out when we got to multiple regression, that's actually n minus k minus 1. Well, it's n minus 2 because there's only 1, because k is 1. Yeah. So n minus k minus 1 is going to be the degrees of freedom we use. We look on the t distribution for 90% confidence interval, and we get a t value of 2.132. All right, and what's that 2.26 number?
Standard deviation. Standard distribution of the sample.
Yep, so that's already given to us. That's not even a standard deviation. We don't have to divide by the square root of n. It's just already spelled out for us in this problem. Standard deviation of the sampling distribution of the sample slope. Yep, it's 2.26. So all we need to do is take 2.13 plus or minus of those, and we've got our confidence interval. On number 9. All right, we good there?
Yes, sir.
Like it? Fantastic. Ready for number 10? All right. So let's do a hypothesis test to determine if the population slope is statistically significant. Let's use a 1% significance level. So when we say statistically significant, we mean that it is significantly different than 0. Because if the slope were 0, that would mean an extra 3 hours spent online has no relationship to more money spent online. Multiply that 3 times 0. If it is something besides 0, then it is a statistically significant relationship. So let's erase all of this. All right. Let's see. The null hypothesis is that population slope is the population slope, this big B, equals 0. Means there's no relationship between the independent and dependent variable. Alternative hypothesis, population slope does not equal 0. Two-tailed test, 2 ways to disprove this. So let's look at how we're going to calculate our t-stat, because we always use t for regression. All right, so what's the difference between our 8.5 sample slope and 0? All right, how big is that difference? Well, it's 8.5. More specifically, we want to know how many standard deviations above 0 it is. And if it's like a half a standard deviation above 0, and we had one of those earlier tonight, we're like, yeah, it's no big deal. That's not anything worth writing home about. That's nothing that really proves something overwhelmingly. If it's like 5 standard deviations above 0, then now we're talking. So what is our standard deviation figure in this hypothesis test? It's actually just given for us because we really don't.
9.5.
Close. Yes, 2.26.
Oh, because it's the slope.
Yep. No
That's a
problem.
little b, right?
Yes. Well, the Andrew, the little b is 8.5. This standard deviation, or maybe you said this. I'm sorry, I misheard. So standard deviation of little b, is that it?
It's
Yeah.
given.
Is that what you said?
Yeah.
Yeah. Okay. Sorry about that.
But that's of the population slope, right?
This is the sample. Little b is the sample slope.
Okay.
Big B is the population slope. So this is 2.26. Okay. So, how many standard deviations is 8.5 above 0? Well, it is 3.76. All right. So we've got our test statistic. Let's do critical values. Is this a one-tailed or two-tailed test? Two-tailed test, right? So we're looking for both a positive and negative rejection region. What is our significance level? Yep, 1%. All right, so we're looking for 1/2 of 1% here, and we're looking for 1/2% here. All right, we always use T for regression, T distribution. What is our degrees of freedom? What's that? 2? I don't think so. Our n is 4, so n minus what's the magic formula, Jonathan?
N minus K minus 1.
Yes. All right. So 6 minus what's K in this case?
How many?
K is number of independent variables.
About 2
2 or 1? Which one?
or 1?
1, yes. 1 minus 1 minus 1. So 4 degrees of freedom. So we need a critical value for 4 degrees of freedom and 0.5% in each tail. All right, so you have 2 options. You could look in the back of the book, or you could look on the answers. I would accept either.
I'm sorry.
Critical values.
Oh, it's 4.604.
Yes, 4.604, negative 4.604. Okay, so what is the decision then? We got a t-stat of 3.76, and we have critical values, negative 4.6, positive 4.6. Absolutely. Absolutely. Good job, Andrew. So, falls within. It's worth noting, though, this seems like a pretty significant t-stat. 3.6. Why is our standard so high? Why is our standard for rejection so high?
Because we use the T distribution, which allows for a little bit more wiggle room.
Yes. Yeah. So t distribution, not only a t distribution, but basically two other t distribution. Yeah, 2 other things I'm looking for as well.
0.01.
Yeah, a very small significance level. That's one reason, and the other why our standard is so high.
Oh, we have 2 independent, the degrees of freedom.
Degrees of freedom is really low.
Really low.
Very small sample size, only 6.
Because we have 2 variables.
No,
Not
because
variables.
one.
We only have 1 independent variable,
Okay.
but the key here is we only have a sample of 6. So it's a very small sample.
Gotcha.
So it would not be unusual for us to get a large extreme value with only a sample size of only 6. If we had a sample size of 30, then we would not have such a high standard for critical value.
Good question.
Yes.
I might be missing something. You have, the sampling slope is the 2.26, but the 8.5, isn't that the population slope? So shouldn't that be a capital B?
This is our sample slope, 8.5.
No, go there. See there? It looks like either a 6 equals 8.5, or it looks like a small b equals 8.5.
Yep, small b. Small b.
It is small b.
Yep. Small b.
Okay.
And we want to know what is Big B. Is it significantly different from 0? Okay.
Kind of.
Yeah. Well, I mean, yeah, it's 8.5 difference from 0.
Yeah.
Question is, how many standard deviations different from 0 is it?
So,
3 point.
okay, so 3.76. So
Yes.
because the 3.76 is within,
Yeah.
then we're not rejecting.
Yeah. It's 3.76 standard deviations, but it needs to be 4.6 standard deviations difference
Rejected.
because we have such a high threshold. We have a high threshold because we want a 1% significance level, and because we have such a small sample size.
Isn't it easier to just compare it and if it's less than,
Compare the
critical value,
compare the 3.76.
4.6.
Yeah. We say it's within this range. Wait, what did I do? Did I do something different than that?
No, it just, too much wording confuses me. I just do less than or equal and then I know whether it's fair or rejected.
All right. All right. We ready for quiz 7?
Yes, sir.
Let's do it. This is the Zach Williams not teaching stats class.
Oh man, exactly. It's not teaching stats.
Let's see if I can redeem myself now.
Oh yeah, this was that class. You're right. That Williams hard, right? What? Oh,
Alright.
straight up. I guessed I was doing that.
All right. So for the first problem, we've got a multiple regression equation, which is asking us to predict home price with technically 3 independent variables. One of them is an independent variable that we're used to, which is square feet, right, in hundreds. So if you have a 1,200 square foot house, then you have 1,200 square feet. And for each 100 square feet, you're going to multiply by $15,056. So your house is 1,200 square feet. Miguel's house is 1,300 square feet. All things being equal, I'm going to say her house is going to sell for $15,056 more. All right, we're going to have an intercept of 234,767. So you add that to your square footage. And then there's these dummy variables, x1 and x2. What do those mean? How do we interpret those?
You interpret dummy variable as 0. It's 1 or 0.
Yep, 1 or 0. In which instance would it be 1? In which instance would it be 0?
I'm gonna give you an indication.
If it's within the same zip code, it'll be a 1. If it's not, it'll be a 0.
Fantastic. So it's just a yes or no. You check the zip code, check the table, 1 or 0.
Remember this question.
And then, so let's look at the zip code, and let's try to think which one of those is the rich neighborhood, which one of those is the middle class neighborhood, which one might be the poor neighborhood.
This would be
Yeah, no, you can figure it out.
Oh,
Look at the regression equation, and then look at the zip codes.
yeah. So the 9802
Is what?
is that x2?
Yeah, but is that the rich neighborhood, the middle class, or the poor neighborhood?
Middle.
Middle.
Which
No.
one? Just tell me which one is rich. Just make a statement.
I think the 98026, the first one with the double dummy variables, is the rich neighborhood.
I like it. Why do you think that?
So it has a positive x1.
Because you don't have to subtract off anything in evaluating the estimated value of that house.
I'll take that. That's not what I saw.
So you put in 0 for the x2, 0 for the x3, and that makes your predicted home price higher
Yes.
because x2 and x3 are negative. So if you live in 98026, you have no negatives.
For, I guess the middle class would be x3.
No, tell me which zip code would be middle
So middle
class.
class would be 98029. Because it has a lower negative in X3.
You think that would be middle class? I disagree with that.
So we have to.
Oh, the other one.
Yeah,
What would be the other one? 9116?
98116 would be middle class.
98116.
The reason why I said we use that one, 98029, is because X2 has a higher negative.
Yeah.
So I didn't want to zero that negative to make it middle class.
Yeah, so I mean, so if you have to put in a 1 for X2, that means your house is $106,748 less in value than someone who doesn't have to put in a 1 for that variable. So
So you want to zero it to be the middle class. The bigger.
I don't know not want. It's just we're just predicting home values.
I'd be totally fine if you left this off
This whole chapter.
This is
All right. Well, let's back up a minute.
Yeah.
So we're predicting home price. All right. There's a intercept component, $234,767. Any home, just for even if you don't have any square feet, technically, your house would be worth $234,700. That many dollars.
Gotcha.
But the intercept, we use it mathematically, but it doesn't have meaning the same way the slope has meaning.
Okay.
It's just the math, so we won't get too caught up on interpreting the intuition there. What we do get caught up interpreting the intuition are the sloped coefficients, x1, x2, x3. So x1, we know that we have, for every additional 100 square feet, our home is expected to increase in value by 15,000. So more square feet, more value. And then, if we have to put in a 1 for x2, which means, if you look at the table, under which situations would we have to put in a 1 for x2?
98029.
Yeah, if we live in 98029, we then put in a 1 for x2. And all other things being equal, that house is worth $106,000 less.
Yes.
All right, if we don't live in that zip code, we put in a 0, and we just ignore that part. If we have to put in a 1 for x3, tell me on what zip code might we live in where we'd have to put in a 1 for x3.
98116.
Yeah, if we live in that zip code, we put in a 1 for x3.
And your house would be $26,726 less.
Yes, all other things being equal. All right, so
So your rich neighborhood would be X3.
no. There's only 3 neighborhoods, and they have 3 zip codes. The x1, x2, x3. Those aren't neighborhoods. Those are independent variables. So, tell me the rich neighborhood.
98106.
98116.
Oh, 98026. Because you're not losing any value per square feet.
Yeah, the correct answer, the rich neighborhood is 98026. Let's make sure everyone, does that make sense, Victor?
Yeah, because you're not subtracting anything.
Yeah.
All right, now tell me the most poor neighborhood.
Let's see,
98029.
Yes, because if you live in that neighborhood, you have to subtract off a big chunk. So you live in that neighborhood, Ellie lives in the rich neighborhood, you have your house, all things being equal, $106,000 less. And in the middle neighborhood, where all things being equal, your house is $26,000 less, is the 98116. Okay, so if I give you the information about how many square feet you have and which neighborhood you have, you tell me what?
The predicted price.
Yep. I'm not going to say anything more than that, but I can repeat that again if necessary. Or even if not necessary, I'll repeat it again. So you tell me your square footage in your house. You tell me what zip code you live in. I tell you the predicted value of your home. And you crank that out and tell me on the exam. We good? All right.
How did we get 429 and 139? I'm sorry.
Sure.
Where did that 20 come from?
All right. So can someone explain where that 20 came from?
It's part of
2,000 square feet.
Yeah.
Got it.
it's part of this, right? There's the line. X1 is defined at 100 square feet for examples of 1,200 feet. X1 would be 12. They gave us 2,000, so you just take away 2 zeros.
So now X1 is just telling me that if it is a certain square footage, I'm adding that?
Yep.
Okay.
Whatever square footage.
So
Suppose your house was 3,500 square feet
It would be 35 times 15.
times 15,000. Yep. Yep. And then you figure out which zip code you live in and do that calculation.
So, I have a question.
Yes. No.
This says correct feedback, incorrect feedback.
Oh yeah, that's just the way Blackboard works. It's
Oh, because
yeah,
it looks exactly the same to me.
Yes,
So I'm
it's-
looking for like,
it's the same. Yeah,
okay.
it's the same. It's
I'm like, wait.
sorry about that. It's so if you give
It's a sanity test.
Say- it's a multiple choice question. So if you got it wrong, you would get the incorrect feedback. If you got it right, you would get the correct feedback.
I'm like,
Okay. All right.
missing a point here?
Number 2.
All right.
All right. Below is an output for regression analysis attempting to link dependent variable y to independent variables x1 and x2 using a sample of 18 observations. Build a 95% confidence interval estimate of the regression coefficients, big B1 and big B2. So big B1 is the whole population slope for 1, big B2 is the whole population slope for coefficient 2. All right, and the x1, x2, I guess we could put those are little b's. We could call those little b's the x1, x2.
So sample.
Yeah, sample slope. Yeah, that would be fair if you wanted to call those little b1, little b2. All right, so little b1 is negative 1.4, little b2 is 1.1, and we have standard error figures. And let's call those standard error figures standard deviation of the sampling distribution of the sample slope. So let's do 95% confidence intervals. Do we use for regression, do we use a z or a t? We use t. How do we calculate degrees of freedom? Tell us, Jonathan.
It's a n minus k minus 1.
Yeah, it's always in minus k minus 1. All right, and what is k in this example?
This is true. There's 2 variables.
Yeah, k is independent variables, and there are 2 independent variables. So degrees of freedom is 18 minus 2 minus 1. Carlos has helped us out with this before.
Huh?
Oh, sorry. Sorry, it's being funny.
15.
15, yes. Yes.
I was listening.
15 degrees of freedom, 95% confidence, and it's going to be a two-tailed situation because we could make a mistake, positive or negative on the slope. If we were to look in the back of the book, 15 degrees of freedom, t-tail test, 2.5 in each tail, we would get 2.131. So, all right, so for the first one, little b1, negative 1.4, we're going to go plus or minus our 2.131 times the standard error. And we're going to get that confidence interval. For little b2 is 1.1 plus or minus the appropriate t value times the standard error of 0.58. And notice that that's giving us a confidence interval for big B1 and big B2. So we've got the sample slope, little b's, or x's, whichever way you want to look at it, and it's inferring that the whole population slope would be the big B1, big B2. We like this. Good there?
We'll just skip the rest
Alright, I'm with you. I'm with you.
I know, which, I won't give up on you. You won't give up on me.
The output below is from a study of multiple linear regression to link independent variable y to x1 and x2. The sample consisted of 28 observations. Alright, so we've got an intercept. We've got little b1 or x1, little b2 or x2. We've got standard errors. Alright, if we needed confidence intervals or we wanted to do a hypothesis test, we could do standard errors. We've actually, in this, we've even got t-stats. And those t-stats, the reason why I felt comfortable giving you this table is there's some homework questions which direct you to understanding that. The t-stat is just a no difference hypothesis test. So if you are a difference between zero hypothesis test. So is the slope 1, negative 1.2, is that significantly different than 0? Well, the t-stat you would calculate is negative 1.364. How about the 3.5? Is that significantly different from 0? You'd calculate a t-stat of 3.125. Okay, so you could look at the t table and find out if that passes muster on the t critical values. You could do that. In fact, you need to for this problem. And you're also given a p-value for that t-stat of slope 1. A p-value of 18.5%. Alright, so let's just go straight to the correct answers. The correct answer is the last one. And let's just read that through and make sure we're comfortable with why that is accurate. Yeah, so for B1, also known as X1, the p-value is 18.5%. Since 18.5% is higher than our 5% significance level, we can't reject the big B1 equals 0 null hypothesis. Is everyone comfortable with that statement?
Since it's greater than
Yeah.
because it is reject, yeah.
Yep.
Okay.
Yeah, so that's saying if we were to do a null hypothesis, saying x1 equals 0, we would not get overwhelming evidence to the contrary. We would get something that happens, say, 18% of the time. We don't consider that overwhelming, so we can't reject the null hypothesis. This coefficient is not statistically significant. For little b2, the t-stat is 3.125. From the table, the critical value for a 2.5% tail and 25 degrees of freedom is 2.060. So let's back up a minute. Let's actually find that t-value, or think about how we would find the t-value. So we've got 28 observations, which is how many degrees of freedom, Jonathan?
25.
25. And we're at a significance level of 5%, 2.5% in each tail. So we flip back to the t distribution, 25 degrees of freedom, 2.5% in each tail, and that gives us a t critical value of, outstanding, 2.060. So if we were to look on the table, we would see that as correct. And we would know that 25, we would know that that t-stat of 3.125 is greater than the t critical value that we found in the book. So we can reject the slope 2 equals 0 null hypothesis. This statistic is, this coefficient is statistically significant.
You're saying that is significant?
Yeah, because it is It's 3.25 standard deviations above 0.
So that means that the null hypothesis is equal to 0.
Yes.
So there's no correlation.
Right. It's not a correlation issue. It's
Or
just,
significance issue.
yes. It's just, is it significantly different from 0?
Okay.
Well, it's 3.125 standard deviations above 0. And we decided based on our parameters that if it's 2.06 or greater standard deviations above 0 or below 0, then we're going to call it significant. Alright, so number 4. Are we good? We're tired, but we're good. Or at least not dead. Okay, so for this one we need to know mean square regression, mean square error, and how we combine those two for FSTAT. So mean square regression is going to be our sum of squares regression, which is 2330. Alright, that's the sum of squares, and it's in the regression part. So it's 2230, and we divide 2230 by 2, and 2 is what?
Degrees of freedom.
Well,
Oh, there are two variables.
yeah, it is degrees of freedom, sort of, but it's 2 variables, 2 independent variables. I would not get confused by that degrees of freedom column. So we divide that by 2, the number of independent variables, how much of the regression each variable, or how much of the SSR each variable explains. Then how do we get this mean square error? Just MSE. Well, we take the sum of squares error, which is 6620, and we divide that roughly by the samples, number of samples.
25.
Yeah, so it's 25. It's roughly this number of samples, but number of samples minus,
Degrees of freedom. Minus k minus 1.
yep, minus k minus 1. In this case, k is 2, 1 is 1, 28 minus 3 is 25. So, alright, so we take 6620 divided by 25, and we get 264. So then, for the FSTAT, remember the name of the game with the FSTAT was the explained variation divided by the unexplained variation. Alright, if that's close to 1, then this whole regression equation that you just calculated doesn't really explain much. But if it's significantly different than 1, then wow, we've got something. We've got explained variation, 1225 in the top, unexplained variation, 264.8 in the bottom. Alright, those pretty different. Those in fact 4.211. So we like that number seems different than 1. Our next step, if we were doing a hypothesis test, would be, or actually, you know what? I guess you all don't need to worry about that because I already told you that the exam questions will be, actually, wait a minute. I think you might have to actually calculate, yeah, the next one you have to calculate an F test. Sorry. Okay, so the 4.211, so we could, if we needed to look on the F table in the back of the book, we would have numerator degrees of freedom of 2, we would have denominator degrees of freedom of 25, and we would have whatever our significance level was, and we could do a reject, not reject scenario there. Okay, are we good there? All right, let's do number 5. All right. So here we've got 2 independent variables. All right, we've got a sum of squares regression of 1828. We've got a sum of squares error of 3282. We've got a sum of squares total of 5110. All right, now pop quiz. How do we get from 1828 to 914?
SS divided by DF.
Divided by
Yes. How do we get from 3282 to 218.8?
Divided by 15.
Yes, divide by 15. All right. How do we get that F value of 4.177?
Divided by 15.
Yes. We divide explained variation divided by unexplained variation, we get 4.177. And the p-value for F is what? Yeah, 3.6%. Yeah, if we were doing a hypothesis test and said we're at a 5% significance level, what would we conclude? Which is, we're not really used to going this fast on setting up hypothesis tests. But what this p-value is, it's saying a null hypothesis that this whole regression equation, all taken together, all the variables, tells us nothing worthwhile.
There's nothing significant.
Yeah, that's a null hypothesis. Nothing significant in this regression equation. The alternative hypothesis is at least one of the coefficients is significant. Okay, and then we have a test statistic that has a p-value of 3%. Now what do you think, Jonathan?
We can reject.
Yes.
Because it's the R0. It's the no hypothesis.
Okay.
Burned out.
Alright.
Burned out.
The p-value is less than the significance?
Yes.
Reject. Okay, so let's go straight to the right answer. It's A and C. Let's quickly read through these and make sure we know why those are right. All right, we can use the p-value for the F to make the call. Since the p-value is 3.6%, is less than 5%, we can reject the all population slopes are zero null hypothesis at this significance level. Yes, because 3% is less than 5%, we can reject the all these are zero. All right, that is A works. Now how about C? We can use the F value to make the call. Since the F value, 4.117, is greater than 3.682, we can reject the all these are zero null hypothesis. All right, tell me how we got that 3.682. It had to do with looking at the back of the book at the F distribution. Yeah, the F chart. And what were our degrees of freedom? So this is the funny one with numerator degrees of freedom and denominator degrees of freedom. So we have the numerator degrees of freedom is number of independent variables, just 2. Denominator degrees of freedom is
N minus 2.
n minus k minus 1. Yep. And if we were at a 5% significance level, we would see 3.682 as the critical value.
Sorry.
Nothing personal. Nothing personal.
No, it's not personal.
All right. Unless you maybe made it be personal. I remember, let me tell you a brief story as we flip to Class A. I remember I sat through one day of a government class in college. And I thought the teacher, the professor, was an absolute idiot. And I dropped his class. And later, he sees me like walking in the hall and says, "Hey, how you doing?" And he says, "I remember you." You know? It's like, guys, I remember you're in my class. It's like, I didn't take it personally that you dropped. It's all cool. And I thought, well, you should have taken it personally. And then maybe you could up your game and teach a better class. Okay. All right.
Nobody dropped this one.
No.
Let's drop it.
Oh, yeah. Good. Yeah. No one dropped this one.
You need
So
to send that message to a few other people.
Yes.
maybe you should have taken it personally. All right. Quiz 8. Alright, number 1. An NBC Wall Street Journal poll asked adults monthly in general, do you approve or disapprove of the job Barack Obama is doing as president? So we've got June 2009, we've got 2010, 2011. We've got approved, disapproved, not sure. Alright, we're going to test the null hypothesis that approval rating is independent of survey date. And we're going to look for overwhelming evidence to the contrary at the 5% significance level using the chi-square test statistic. So, if approval rating is independent of survey date, what would you expect those numbers to be? Some of them would be all the same. Which ones would be all the same? Alright, well let's turn the page and let's look at expected. For about an hour ago. Or 2 hours ago. Alright, so look at the expected values and tell me which ones are the same and why you would expect those ones to be the same under the independence hypothesis. Yeah, so approves would all be the same. Disapproves would all be the same. Not sures would all be the same. Why would those be all the same under the approval rating is independent of the survey date hypothesis? Yeah, that's true mathematically, but just tell me the intuition there. Alright, it's late. Go ahead, Carlos.
Why? Because everything would have stayed the same because it was expected to stay the same.
Yeah,
From the original observation.
Yeah, if date is independent of approval, we would expect the approval to be the same at all 3 different dates. Right? It doesn't matter whether it's 2009, 2010, 2010. You're still going to have the same amount of approval, disapproval, not sure for Barack Obama. That's the null hypothesis. The alternative hypothesis is that date matters. The date is not independent of approval rating, meaning the date means more or less likely to approve or disapprove. So, expected, approved, disapproved would all be the same on every date. So let's find the difference for each cell. And the difference is observed minus expected squared divided by expected. We do that 6 times. And we calculate our chi-squared stat of 113/10. And we need to know our critical value at the 5% significance level. To do that, we need degrees of freedom, which is rows minus 1 times columns minus 1. So 3 times 1 times, 3 minus 1 times 3 minus 1. 2 times 2 is 4. We look in the back of the book, chi-squared, 5% significance level, 4 degrees of freedom. We get 9.488. And you reject. Yeah, it definitely matters what date you asked. It would definitely affect the... So I would definitely queue this up in Excel. Some of the students Monday night were very frustrated by the Excel exercises. I don't know if you all had the same experiences.
No.
I would. You were frustrated by it?
Because you have to become an IT person. Because the Excel that you have, if you don't know macros, you have to install and add on. So just using Excel.
Yeah, that was part of the reason why I said for this week's Excel, do what helps you. Don't worry about it if it doesn't. We'll do what you did on the quiz. It seems like most people were pretty successful on the quiz. But one way I think is pretty straightforward is just do 3 different tables on Excel. Do your observed, your expected, and then manually type in observed minus expected squared divided by expected. You can even manually type that in 6 times, or if you know how to do with the $ thing, you can do it that way. Okay. We can do the last one if you want, but it's the same thing. Alright. I'll be around if anyone wants to go over the last one or any other questions you have.
The finals.
Yeah, the final will be on Blackboard, just like all your other quizzes. Yeah, you have to take it during class time. 2.5 hours.
3 hours.
2.5 hours. Oh, sorry. Alright, so a two-tailed test because the slope is 8.5. This slope. So, yeah, no, this is the sample slope. We estimated this for like time online, we would say for every hour you spend online, your estimated is If this program is like 22, then for every hour you spend online, say you spend 3 hours. Now this could be negative also. Like this were negative 4. So anytime you spend 1 hour online, I would say you spend $4. Well, we don't usually do tell because slope could be positive or negative. Yeah. So, and we want to know if it's different from 0.
I need to get
It could be negative different from 0. It could be positive.
So there was the one.
Yeah, what happened also? Can you say no so?
There's not a one-tailed test for slope. Yeah, because slope could be positive or negative, and we just want to know. We didn't know whether it was going to be positive or
Just
negative
tell
before
them.
we
Be
started
like,
this.
yo, I didn't even look because you haven't put my case in.
That was exactly my point.
I just say, listen, I apologize, but I hope you're not gonna doubt me.
Keep
Oh.
proceeding.